I want to share a new thing I learned about the Windows Kernel TCP/IP stack. Very interesting when certain implementations of whether it's the kernel or certain application implementation decisions, it's always very interesting to see how different parties interpret certain proposal or RFC and implement it. In this particular case, Windows versus Linux act completely different. Like so what's the story? So let's summarize it and then go into a little bit more detail. So to establish the TCP handshake, right, to connect to a host, you specify the destination IP address, right, and the destination port that you want to connect to on that host that this IP addresses basically belongs to. So first, what we need to do is send that SYN request to synchronize the client and the server sequence numbers, right? So you send the SYN, and the SYN will go into a segment with the destination port, let's say port 80, right? This will be encapsulated into an IP packet. Well, technically, a segment only have port. The IP packets will have the destination IP, right? And then through the internet, we'll route all this IP packets. We don't deal with ports often when it comes to the internet. We just deal with the IP, the raw IP packets. The destination IP is important and the source IP is important. Yeah, we use the port for certain algorithms to make the path sticky into one place, but more importantly is the IP address, so we can route, right? So this is the beauty of the IP protocol, where we can eliminate billions of networks and go exactly to the network that we want to go, right? This is all the art of the subnet versus the host, right? This is all that I discussed in my networking course, and it's also available in videos that I put on YouTube. But so once you reach that IP packet reaches the host, right? Let's not take the case where the host is unreachable at all, right? So we are routable. We reached the IP packet, reached all the way to the host. The first thing that will happen, the IP packet will go to the NIC, and then it depends whether you have a smart NIC or a normal NIC. It will basically copy the content of this packet to the Windows or Linux or Unix or Mac, whatever the kernel is, memory. We copy the data there. That segment's copied in the kernel. And then there are checks that happen there in the kernels. Right? The first thing, well, most important thing is there a corresponding file descriptor, or in Windows, an object, a WinSocket in objects, right? WinSocket, by the way, is the first, socket programming ever done back in the late 90s. WinSocket, that's for Windows, right? So we check, is the destination port actually, now, yeah, the IP is there, we reached, but wait a minute, you're trying to go to port 80? Is there a listener? Is there a process or processes? Because, yeah, one port can be listening on multiple processes, right? Multiple processes can be listening on one port if you enable the socket option, port reuse. But in general, right? So you have that. We reached it. But guess what? There is no listener. What do you do in this case? Well, all of this stuff is defined thoroughly in the RFC, in the 1981 TCP RFC. So you get that, and then the kernel, right, is supposed to reply back. So this is the backend kernel, not the client, right? So there's always the client kernel and there is a backend kernel. Both are talking in TCP/IP. Because the TCP/IP is always implemented at the kernel level. We at the application know nothing about it. So, and this might cause problems, as we're gonna see in this video, right? So now we reached it, but guess what? There's no port 80. So what do? RFC says you have to send back because you reached. Might as well acknowledge this SYN that you sent us, but we gotta have to send back an error. and reset RST. You send back a new segment to the client, an actual reply, if you will. This is a reply. This is the server telling the client that, hey, I exist, but dude, there's nothing here. Whatever you're trying to connect to, there is nothing. So you're sending a reset. And this tells the client that, oh, okay, that means the host is there. It's just the port is unavailable for one reason or another. It could be there is no listener. It could be that I'm so overloaded I couldn't accept connection, so I sent you a reset. Or I waited and I sent you a reset that I don't have enough. I don't know. Maybe the maximum number of file descriptors exceeded and I cannot connect. Right? Sorry. So you consider this. So this tells the client this knowledge that the server was reachable, but the port you're trying to connect is not. And here's where things come interesting. The kernel client-side implementation of TCP/IP says in Linux, receive the reset. What do we do in Linux? We just tell the application. We just bubble it up, as we colloquially say in programming. We bubble up the error to the higher stack. And we say, yo, there's a reset. And it ends there. The kernel's job is done for the Linux kernel. That's it. We don't do anything else. And then the application can do whatever it wants with this knowledge. And now you might say, Hussein, I don't do anything with resets and all. Well, because we are so used to building on top of stacks, on top of libraries that are, hiding all this stuff from us. Whether it's good or bad, I'll leave it to you. But it's just because we're just being, cuddled by these libraries, we have no idea what's going on. Right? We've been led by the hand all the time. But essentially, the application can decide whether to retry the connection or not. But here's what the Windows do. What the Windows kernel does. This is since 1995. This is the Windows 95, right? Specifically. What it does is, because of what I said, well, servers can get overloaded. The host port could be, down for a moment. The service has been restarted. Especially back then, there was no concept of, zero downtime or anything like that. It's not working. Just restart the machines. Planned outage, wherever. It's fine. Scheduled maintenance. That's fine. So you restart it and then it will come back eventually. So what Windows did, and you can disagree or agree with this, they put a retry where in the kernel. The kernel, when it received the reset, it is being told that the host does exist, but the port that we're trying to connect is not available. Now, whoever designed the RFC for TCP didn't add more error codes reset, reset 1, that means is this, reset 2 is this. I really don't know if there is multiple reset versions, but reset 3 is this, reset 1 is overloaded, reset 2 is this, a port is not available at all. Reset 3 says, it's temporarily not available. It's this will become like an HTTP server code at this point. But, there's just one error message, reset. So what happened to the kernel, the Windows, will retry it. So, all right, wait a minute. Let's just wait for a little bit more. And so we will wait for 2 seconds, exactly 2 seconds. And this is configurable with a rich key. And then it will retry the send, right? It will send the send back, a new send with a new segment. Because maybe now it's available. And of course, if it's not available, it will try again. If it's not available, try again for maximum of 3 times. And both the 3 and the 2 seconds are configurable in a rich keys. So this is what's happening here. You might say, who cares? Why would I ever connect to a port? If I connect to a port that is not available, even if you can do it on Windows right now. If you have a Windows machine, just go connect to, do a curl or telnet to a port, to a host that you know it exists. I don't know, Microsoft.com, and put a port, I don't know, 9999. Hopefully that doesn't exist. You will see that the response comes back in 2 seconds. Okay? In Linux, it comes back immediately, right? And the only cost is the cost of the basically round trip, right? To go back and forth, right? So try it on localhost. And this is what I want to discuss. Right? So let's jump into this Daniel Stemberg. This is where I learned all of this stuff from this guy, to me, I call the Daniel Stemberg, who is the creator of curl, he's the ultimate, guru when it comes to front-end engineering, as I understand front-end engineering. They built the ultimate front-end machine. He understands everything that goes to the front end when it comes to command line, at least, right? So, because curl is a front-end application, right? It's a client application, right? I know we refer to front-end usually as web applications, but I kind of distill it back to its basic, beautiful, fundamental level, which is this TCP stack, right? And in the future, when we implement Quick, it will be UDP/Quick and HTTP3. But yeah, let's jump into this article, read a little bit, and discuss. All right, so this comes from Daniel Stenberg, right? And I'm not gonna read the whole article because I'm gonna reference it to you, because we have to give, credit to the author of this. This always follow, Daniel. I always learn new things that I will never ever dream of learning by myself from this guy. So, title: Slow TCP Connect on Windows. Now that I summarized all of that mumbo jumbo about the difference in kernel, right? Of the Windows kernel versus the Linux kernel. This is what's the difference now. See, this is where it really matters, right? Because, you connect to a port that doesn't exist, you just quit. You just do Control-C and then you move on with your life, or just refresh, right? But what if there is another RFC that also does retries? This is where it gets very dicey. Let's do it. Let's go into it. Let's jump into this. So, I have this tradition of mentioning occasional network-related quirks on Windows on my blog, so here we go again. This round started with a bug report that said, curl is slow to connect to localhost on Windows. So very beautiful title. This is a very, I would give this bug title 9 out of 10. I love it. Because it has exactly describe what is the behavior curl. I should start a show where I rate bugs. No. It has the behavior connect. It has the platform Windows. It has the destination localhost, and it has the application curl. Curl is slow to connect to localhost on Windows. 9 out of 10. It is also demonstrably I cannot pronounce that word. It is also demonstrably, I think you made up this word, Daniel. Sorry, this is not a word. Demonstrably true? Okay. This is also demonstrably disturbingly true. I'm going to change the word. The person runs a web server. I have dyslexia. The person runs a web service on a local IPv4 port and nothing on IPv6 port, right? Of course, Daniel always assumed everybody knows what he's talking about, which is not always the case, because I always didn't understand what he was writing, maybe like 5 years ago, until I gained a little bit of a knowledge, right? because he's way there, you know, when it comes to this. So he doesn't explain fundamentals and basics. So let me talk about this a little bit. So localhost is a host name, is a DNS entry. You can think of it this way, right? And it's useless. The string localhost is absolutely useless for TCP. It doesn't mean anything. Yeah. So you need to convert it to an IP for it to work on TCP. You cannot just, although you technically using curl, you type HTTP : localhost, this down the drain, down the stack gets translated to an IP address, right? The trick here is we have two protocols. We have IPv4 and we have IPv6 or this net, right? So the problem here is which one to connect to. IPv4 or IPv6? Hussein, wait a minute. Well, localhost, I know that it's 127.0.0.1, and that's the IPv4. What is the IPv6? Well, it's : 1, right? And that is basically the loop back IPv6 version. And if you have IPv6 enabled, which I think it's always enabled at this point in 2024, you get both. So localhost, if you do a DNS lookup, it will resolve to two. It will resolve to : 1 and 127.0.0.1. Which one do you want to connect to? Right? Which one? And this is where things started to get interesting. The moment you get a choice, the moment you get, and this not only applies to localhost, applies to normal DNS queries. If you do a DNS query to Microsoft.com, I'm hang up on Microsoft for some reason now because of Windows. If you go to any site, Twitter.com, X.com, it gives you have to do a DNS, right, to get back IPs. You get a list of crap. You get A record, A. A record is the IPv4. You get A, which is the IPv6 IP address, and you might get like 3 or 4 of those. You might get a text record, which is for, I forgot what's that, TXT, and you get MX, which is for the email, and you get so much stuff like a alternative service for HTTP3 if that's supported, right? And you have, of course, DOH, DNS over HTTPS on your configure, right? So do you have to? I'm not sure actually, but yeah. So when you get that, you get a choices. You get a bouquet of IP addresses. Which one do you connect to? And here is where there is a beautiful RFC called Happy Eyeballs. A weird ass name, Happy Eyeballs. I'm pretty sure it just means something in like colloquial English language that I don't know about. But Happy Eyeballs essentially means, as a foreigner who doesn't speak, is not my first language, it doesn't mean anything. Happy Eyeballs, like someone is happy to look at this. I don't know. But what it means is you pick the IPv6 first before IPv4. You favor IPv6 first. Now, what algorithm to choose? There is 2 versions of this RFC, the Happy Eyeball. There is the old version where you retry IPv6 and you retry again and you retry again, and then if it failed, you try the IPv4, right? So that's in itself. Forget about the kernel bug for a minute now. For the Windows, not bug, the behavior for Windows. Forget about it for a second. Happy Eyeball tells you to try the IPv6. If it fails, go to the IPv4. And the new version, which curl doesn't implement, by the way, it tells you to establish both concurrently 2 connections, which is of course resource intensive, right? Connect to IPv6. If it fails, connect back to IPv4. No, connect to both IPv6 and IPv4, right? Connect to both of them at the same time. Send 2 sends, right? And then wait for wherever it comes, right? So if you get a reset on the IPv6, just ignore it and continue with the IPv4, right? And then continue with IPv4. If you both succeeded, which sometimes you will, you have to close the IPv4 and continue the IPv6 connection, because we want the IPv6, the new and shiny things, and it's optimized, and the headers are efficient, and it has like billions and billions and billions unlimited, IP addresses What else? Has a lot of benefits. You know, I can't remember all of them right now. So we understand now. Now we go back. With that knowledge, let's go back to the article. And, all right, it is also disturbingly true. The person runs the web servers on a local IPv4 and nothing on IPv6. Now, if in the case that you're listening on localhost, you just decided to ask Node, listen on. If you ask Node, you cannot ask Node to listen. Can you ask Node to listen on localhost? If that's the case, I think Node will listen on both IPv6 and IPv4, right? In that particular case. If it takes a string, I can't remember if you can give Node.js or Bun or whatever higher level library a string. Eventually, Bun or Node or PHP or wherever the framework needs to understand what that means and also listen on an IP, because it doesn't make sense to listen on a string, right? So if you did listen only on IPv4 127.0.0.1, what will happen is basically you're listening specifically on an IPv4, right? There's nothing on IPv6. So if you try to connect to : 1, nothing will happen on port 80, although you are listening on port 80 or 8080 on IPv4, right? So that's the situation you have. Right? And if that happened, it takes over 200 milliseconds to connect to it. Right? You would expect it to take no less than a number of microseconds, as it does on just about all other systems. Right? So he's saying it takes about 200 milliseconds. Because that's what's happening here, right? So that's the command. He's showing the command here. It's localhost 4567. Now we're connecting. Buckle up. This is getting worse. But first, let's take a look at this exact use case and what happened. Right? This is all I now explained. This is all the happy eyeball things, you know. On all systems except for Windows, where the IPv6 TCP connect at attempt sends a send to the TCP port where nothing is listening, right? Because we're talking to the IPv6. We're sending a TCP send. It gets a reset back immediately, right? Because IPv6, the IPv6 : 1 in this particular case does exist, but there is no port. So we send you a reset. In all systems except Windows, we get back what? Connection refuse. We get a reset, and then you get a connection refuse. So what do? We switch back immediately to attempt to IPv4. So this whole thing happens in few milliseconds. You know? On all systems except Windows switches over to IPv4, and this whole thing happens in few milliseconds. All right? The failed IPv6 attempt is not noticeable to a user. And here are some diagrams showing what it was going to have normal handshake, right? This is where a refused TCP look like. You send a send, you get back a reset. Talked about that. Now, connection on Windows. What happened on Windows, right? On Windows, I'm going to immediately go to the diagram. On Windows, we explain what happened. We connect to IPv6. Guess what? That's because the happy eyeballs tells us you have to connect to IPv6. You send a send. What do you get? Immediately, the kernel, the server or the backend server kernel sends back a reset. In this case, it's the localhost. So it's the same kernel, right? We send a reset. But guess what? Windows will say, wait a minute. We get a reset. This is IPv6. I'm just going to delay for 2 seconds just because I feel like it. That's deep into the kernel. The application have no idea. Curl as an application have no idea. Browser as an application have no idea that Windows is doing these 3 tries. It's like you're calling a function and the function has a loop. Right? And it's doing all this stuff. Right? So it will try again and then again and again until it responds back after a few seconds. It depends on the delay and those stuff, 2 to 3 to 4 seconds. And then only now curl got the fact the knowledge that IPv6 is not reachable. Only now, after 3 seconds, it knows that IPv6 is not reachable, so it kicks the happy eyeball algorithm to switch back to IPv4, which then connects immediately, which works. So in this case, if you only listen on IPv4, but your client is using localhost, in this particular case, to connect, you're gonna hit that slowdown every time, which really sucks, right? I don't know if there's caches, and probably curl will cache or the application. And this is not really curl, any app, right? If you have, I don't know, think about an app like what browser, Node.js. You're listening on 127.0.0.1 port 8888, right? And then, but then in the browser you would type localhost : 88. In this particular case, what will happen is happy eyeball will kick in. The same thing. We'll try IPv6. If you're using Windows, you're gonna see it, and I see it all the time. I got it to explain until now. Every time, localhost will be slow in this particular case. If I'm listening to a IPv4, I was like always not able to explain this, but now it's perfectly clear that this is what's happening. Windows is retrying, and the app has no knowledge about it. So now get back all the way. This gets result, and then what do? Eventually, we switch back to IPv4, and then everything connects, and everything is happy. So you'll feel it sometimes. And of course, the browser is smart enough to cache that. Okay, yeah, last time we checked connect to IPv6, it didn't work, so I'm gonna cache the fact that the service is not available, so I don't have to retry it. So things like that. The browser definitely have done that. That's why I explained when I can refresh the page, it's faster, right? The first time I visit is takes 2 seconds, at least in Windows, right? Linux doesn't have this problem, right? Only Windows. Linux, let's be careful here. If you have a Linux server and a Windows client, you're still gonna see this problem, right? It's the problem with the client code, not server code. Make sense? Right? You will not see this problem if you have a Linux client. You will see this problem if you have a Windows client app. Okay? Isn't this stuff just amazing, you guys? I just love this stuff. 面白いですね. Really, really stuff. Okay, so yeah, let's go to the other article that I'm gonna reference all this stuff, by the way. And if you're listening on the podcast on Spotify or Apple or all that stuff, you're gonna find it in the show notes. If you're on YouTube, you're gonna find it in the description below. Isn't it? So here's the rich key. If anyone is interested, but use it with a Pugsley. Use it with a grain of salt. Okay, this rich key. You can change these maximum connect transmission and the other parameter. What is it called? The max connect retries. You can change those if you want. Okay? It's in the localhost system current control set services TCP/IP parameters. So you can change this. But guess what? This is a global change, and if you change it, all apps will read that value and it will respect it. I mean, not all apps, the kernel. There's one kernel running on your machine, right? So that basically will behave as that, right? What happens if you have containers, though? Because containers share the kernel. If you have like Linux containers, then you're using the Linux kernel. If you're using Windows kernel containers, then all your containers will inherit this property as well. I think. I never tested that, but I think that's what's gonna happen. So that's just something. Regardless, watch out for changing this, because all your apps will just all of a sudden sometimes you'll see something breaking, because this has been there since the 90s, you guys, right? Very long time ago, right? Very, very long time ago. So apps have been built relying on these retries in place to function on Windows, right? So changing this might break other apps, because some apps will just, imagine just not retrying. If you don't retry, and the app is not designed to retry because it had the luxury that the kernel is always retrying for it. And you can argue this is lazy, and I'm not gonna hold it against you, to be honest. But lazy programming. But yeah, if you don't retry in the app, and your kernel is retrying for you, your app just works. So if you change that parameter and it change to 0 retries, for example, and the app try to connect, and for some reason there is a glitch, the port is not available, and received that, it will just, it won't know what to do with this. It will freak out, and it will just maybe crash, right? Or just don't do anything. The other thing I want to end this before I end this video is a little dark here, but yeah, it's a little bit dark here. Sorry, I'm gonna work on my lighting. So the other thing is I differentiate between port unreachable versus address unreachable, right? If you send a SYN to an IP address, and that IP address is not routable, there is no one to reply to you to tell you that the address is not routable, right? Because, well, you will eventually either time out, or you might get an ICMP message, and I talk about that in my network course. Check it out if you're interested. This is the Internet Control Protocol information messages that you get the router, because IP packets, every hop the IP packet goes through, every router, we decrement the TTL in the IP packet. So okay, we start with, I don't know, value 128, right? And then every router, 127, 127, and this is how basically trace route works. If you think about it, right? We until the router that decrements it to 0 will basically drop the packet, and if ICMP is enabled, it will send back something saying, "Boo, go. ICMP host not available." It will send it back. Now, whether this packet reaches back or not, that's a different story altogether. So if you did get that, then you understand that the host is actually not reachable. If you timed out waiting, that's different than not responding at all. I mean, if you timed out waiting for a response, even for a reset, that is different than actually receiving a reset. A reset means that the host is reachable because, hey, it replied to us with a reset. This is like another argument I get with people, that a 404 error to me is also a response, right? Because the server is reachable. It just returned back an error for you, right? So to me, as a backend, 404 is not an error, like, well, you can argue, again, this is all semantics, right? 404, yeah, the backend is actually explicitly got a message, looked up a file, couldn't find it, and replied back to you with a beautiful response HTTP message. Nothing wrong with it. It has a TCP segment. There is a body. There is a body. Yeah, there is a body. There's a headers in the 404 message, and now the client treats it as an error. That's a different thing, right? But to me, it's just a message. And that's also another argument, right? Whether fetch, I think, versus Axios. I think Axios treated as an error and raises an exception versus, this is very controversial. People get very boiled up with these topics for some reason. Yeah, I don't really mind, but yeah, a fetch treats it as a response. It's not an error. Right? So it will just treat it as a response and will send you a nice response. Hey, the server responded. What would it respond to? 404. Yeah, so this is the same thing, right? Reset actually send you a response back, It's just it means, hey, the server was reachable. It's just hey, there's nothing there. The port you're actually trying to connect to is not there. All right, guys, that was like a little bit of a long video, but I thought I'll talk about this because I love this stuff. I love learning new things, and I don't love learning in a sense that I seek learning. The learning comes in to me, right? And just naturally, when it comes, you grab it, So everywhere, learning opportunities are everywhere, flying, like this, It's everywhere. You just need to grab it, If you don't not in the mood to grab it, that's fine. Also, don't beat yourself up. It's okay. It's okay not to always be in the mood to learn and improve. That's fine. Just relax. Be now, here, in the moment, and live. Just live. All right, guys. See you in the next one.